A few more examples of alternating series in the alternating series test. Series n equals 0 to infinity, negative 99 over 100 to the n. This actually looks like a geometric series that we saw earlier in the course, and it is a geometric series, but we're going to use the alternating series test. The only detriment of the alternating series test is that we can't easily find the sum of the series, like we could with a geometric series, the a over 1 minus r sum. However, let's go ahead and see if we can determine, first of all, whether the terms are decreasing, and then secondly, whether the limit is going to go to 0. All right, so we're going to say that a sub k is going to be equal to 99 over 100 to the kth power. All right, so we just get rid of the minus because we know that if n is odd, we're going to have a negative term. If n is even, we're going to have a positive term as part of the sum. So let's just go ahead and see what happens when k equals 0, k equals 1, k equals 2, k equals 3. All right, so let's just see whether we feel like it's going to be non-increasing. Now, clearly, when k is equal to 0, we get 1. Okay, that's easy enough. When k is equal to 1, we get 99 over 100, which is 0.99. And then from there, we could just go ahead and use our calculator. All right, so I'm just going to say quantity 99 over 100, and I'm going to square that quantity. All right, and I get 0.9801, and I'm going to say 99 over 100 raised to the third power. Okay, so this parenthesis doesn't like me. Let me get rid of that. All right, let me try it again. I think I forgot to get out of the denominator the first time. All right, I get 9703. So clearly it looks like it's decreasing. Okay, if I just tried it one more time and instead went to the fourth power. All right, and this is what you guys should be doing in your calculator, is just making sure that it does become decreasing. Okay, so for k equals 2, we got 0.9801. And for k equals 3, we get 9703. Okay, so it seems like that it's going to be decreasing. Okay, so if this is part 1, where we just make sure that it's going to be non-increasing, or in this case decreasing, we look like that we're good. Now, second thing we're going to do is we're going to take the limit as k approaches infinity of 99 over 100 to the k. And another way to think of this is to think of this as 99 to the k over 100 to the k. Right, so this is going to be lim of k approaches infinity of 99 to the k over 100 to the kth power. All right, and of course we could divide everything by 100 to the k, but that's going to get us the exact same thing that we started with. Okay, now think about this. 99 to the k over 100 to the k is going to keep, the denominator is going to get bigger than the numerator. All right, so clearly, because the denominator is going to be greater than the numerator, okay, in all instances, that means eventually this will be equal to 0. Okay, so both of the cases, so we're going to say by case 1, or we could just not even use cases, we could say by 1 and 2. Right, just because those are our two, so I and II, the original series, which was n equals 0 to infinity, negative 99 over 100 to the n, converges. All right. Now, a second example, this one's a little bit sneakier. We have minus 1 to the n and square root e to the n. All right, so first thing we do is let's just change this into a k. So absolute a sub k is going to be equal to, we get rid of the alternating factor, and that's going to be k squared over e to the k. And let's just figure out what happens when k equals 1. Okay, so again, we always start with the lowest down, and then k equals 2, k equals 3, k equals 4. All right, so we'll just do it for the first maybe 4 values. And usually if we could see that it's decreasing for the first 4, then it's most likely going to be at least condition 1 is going to be upheld. All right, so we're going to say 1 square divided by e to the first power. All right. And it's going to be 0.3679. Okay, now I'm going to do the same thing, except I'm going to plug in 2 now. All right, so we have 2 and the exp of 2. And it looks like it's going to be increasing. All right, so that's not good. Let's try it again for 3. So we have 3 square divided by exp of 3. All right, and it looks like it's coming back down again. All right, and 4. So it's going to be 4 square and then exp to 4. All right, and it's coming down again. Let's just do 5 and 6 just to make sure. All right, so 5 and 5. All right, so that one's better. So it looks like that maybe starting at 1, we have a 2 and then we have a 3. All right, or sorry, we have a 3 and then a 5 and then a 4 and a 2. It looks like it's going back down. Again, let's just do it one more time. All right, so 6 and 6. So that's 0.08. So even though it goes up for the first term, it looks like eventually it's going to be decreasing or non-increasing. All right, so for k equals 1, I'm just going to write out like maybe the first 6 just to show. So we get like 0.368, and then it goes up 1, 541, right? But then we have 0.448, and then we have 0.293, and k equals 5 and k equals 6. All right, so I got 5, I got 0.168, and then for k equals 6, 0.089. Okay, so it looks like that even though we have 1 increasing here, eventually over the long term, it looks like that it's going to be non-increasing. Okay, so let's just say other than for k equals 2, all right, it is non-increasing. All right, and of course, we really care about what's happening over infinity, okay, not just for like that one little term there. All right, so it's okay if like maybe one term is going to be increasing, but then as long as it goes down for the majority of the terms after that, or for all terms after that, then it's going to be okay. All right, now next thing we have to do, and this is I, and we have to show that the limit goes to infinity. So we're going to take the limit as k approaches infinity of k squared over e to the k. And unfortunately, if we try to divide by e to the k, we're just going to end up with what we started with. But notice if you use direct substitution, you get infinity over infinity, which means that you have an indeterminate form, which means that you can use L'Hopital's rule. All right. And remember, L'Hopital's rule says you take the derivative of the top and the derivative of the bottom. So when I do it, I just put an L in the circle. And now I'm going to have the limit as k approaches infinity, derivative of k squared, 2k, derivative of e to the k is e to the k. And once again, by direct substitution, we have infinity over infinity. So we're going to use L'Hopital's rule one more time. And we have the limit as k approaches infinity of 2 over e to the k. Again, derivative of the top, derivative of the bottom. This time by direct substitution, we get 2 over infinity, which is going to be 0. All right, so it looks like that it's going to hold up, except for this k equals 2, but that's okay. As long as it's only one value and the rest of them are decreasing, then ultimately it is going to be a convergent series. All right, so we can say by I and I, our series converges. All right. Now this is a really sneaky one. Okay, this minus 1 to the n plus 1, n to the 1 over n. All right, so first of all, let's see if it's going to be decreasing, and then we can find the limit as it goes towards infinity. Now, in this case, absolute ak, is going to be equal to n to the 1 over n. There is a much better test for this, which we're going to see in the next section. All right, but for right now, since we don't know that, this is what we're going to use. Okay, and by the way, this should be k to the 1 over k, wrong variable. Okay, so it's going to be k to the 1 over k. All right, so we're going to have k equals 1, k equals 2, k equals 3, and k equals 4, k equals 5. All right, and since we're using our calculator, it shouldn't be that big of a deal for us to illustrate that. All right, so let's see what happens. All right, now we know what's going to happen with 1. That's just going to be 1. That's easy. Then this becomes square root of 2. All right, 2 to the 1/2, and we know square root of 2 is 1.41. All right, and of course, if you don't trust me, you just go to your calculator. And what I'm going to do is I'm just going to go ahead and just say 2 raised to the 1 over 2. All right, and we get 1.41. All right, and so the good news is now we can just copy and paste this, and we can just change the 2's to a 3. All right, and that gives us a little bit bigger value. All right, but remember, it's okay for like 1. All right, but let's see if it goes back down. So it looks like it goes back down for that one. Let's try 5. All right, and that one goes back down. Let's do 6. All right, that one goes down. Let's try 7. All right, and that one goes down. Okay, so other than this one little blip right here, okay, where we go up by 0.03, the rest of it looks like it's going to be decreasing. Okay, so k equals 3, that's going to be 1.44, and this was 1.41 again. For k equals 5, I got 1.38, and k equals 6, I got 1.34, or 1.35, excuse me. And for k equals 7, I got 1.32. All right, so the only one that looks like it did anything was k equals 3, but after 7 of them, we can pretty much suggest that we're going to get non-increasing. Okay, so let's say though k equals 3 increased, in general, the terms are non-increasing. Okay. And that's important because if they are continuously increasing, that means that we're going to add up to a really big or a really small value. Okay. Now, the trickier part of this problem is being able to find the limit. Okay, so we're going to take the limit as k approaches infinity of k to the 1 over k. All right, so this is a really tough one because if we do direct substitution, we get infinity to the 1 over infinity. All right, and that's not necessarily a good thing. All right, so what we're going to do is we're going to do this trick where we're going to say we're going to take the limit as k approaches infinity, and we're going to say that y is going to be equal to k to the 1 over k. All right, we might have done this in another section. And we're going to introduce a logarithm. All right, so we're going to take the limit of y is equal to the limit as k approaches infinity of k to the 1 over k. We're going to introduce a logarithm. Okay, so lim as k approaches infinity of ln y equals lim k approaches infinity of ln k to the 1 over k. And we know the trick is that we can move the 1 over k in front. All right, so I'm just going to hold on to this. All right, so let's box that, and we're going to star it. So we're going to bring that back down. This now becomes lim as k approaches infinity of ln k over k. And we know that that's the same thing as infinity over infinity, which means that we can use our good friend L'Hopital's rule. All right, so now this becomes lim as k approaches infinity derivative of ln k, 1 over k, derivative of k, 1. So this is really going to be the same thing as the limit as k approaches infinity of 1 over k, and that's going to be 0. All right, so now that is not the limit, okay, because remember, the limit as k approaches infinity of ln y is now equal to 0. Okay, so there's like this transitivity that it was equal to. All right, well, to be able to solve, we're just going to raise both sides to the e power. All right, and by the way, this is a limit as k approaches infinity. That has nothing to do with ln of y. All right, so y is an independent variable of k, so we can do whatever we want. It's not going to do anything. So now we're going to get the limit as k approaches infinity of e to the ln of y equals e to the 0. And that means that the limit as k approaches infinity of y is going to be equal to 1, which is clearly not equal to 0. And that's our second condition right there. Okay, so remember, our first condition looked like it was okay, but our second condition, we need 0 as the limit. But we didn't get 0, we got 1. And so that means that this series diverges. Okay, so we can say by II, our series n equals, I think it was 1 to infinity of minus 1 to the k plus 1 or n plus 1, excuse me, n 1 over n. So it's going to be n plus 1, n 1 over n diverges. All right. Now, we are going to see an easier way later in the course to try to tackle this one. All right, but for right now, this is all we got. Okay, so those are the alternating series tests. Now, to conclude this section, we're going to look at what we're going to do to determine, even if you have a convergent series, to determine if it converges absolutely or it converges conditionally. Okay, so that's going to be in our next video.